Testing 1 2. Okay, everybody, please wait for 5 more minutes. We are waiting for others to join. We will start soon.
Good morning, sir.
Okay, uh, I think most of you have joined. So, welcome everyone to NOX 2021. First of all, I would like to introduce you to ourselves. We are from ISER Barampur, a research institute at Barampur, and we represent a club, the Astronomy Club named Naxatra, to all of you. After that, the meaning of NOX, most of you should must have not have thought about it. The name N 2021, that is Naxatra 2021. NOX means darkness, and astronomy is light for its darkness. And then 2, that is the second edition, IB, Iser Barampur. So with this, I think we can start everything. The day one constitutes of activities and talks related to sun, and I hope you enjoy it. I won't take much time. So Baibhav, tell me when you are ready.
I think
Okay, so
Anamika and Khusbu will be starting.
okay, so you can start presenting. I would like to mention one more thing. During the talk or presentation, no one should unmute their mics. If you have doubts, type it in the chat box. We will be there to answer you. Our team is there. But if there are some major doubts that can't be answered in the chat box, we will give you time at the end of the talk so that we can answer them. So disruption is not allowed, but yes, be interactive in the chat box. Okay, so Khusbu and Anamika, you can take over.
Okay, Bhaiya. Hello, everyone. I think you all are safe in your home. Okay, so let's start. This is Khusbu Suman along with Anamika Das, Vaibhav Srivastav, and Nabendu Mishra. Gonna start this talk from the center of our solar system, the Sun. Before that, let me give you an overview of what we are going to learn today. First, I will explain you about the real color of our sun, followed by an interesting activity on how to make a pinhole camera by Anamika. Then Vaibhav Bhaiya will explain you more into the secrets occurring inside our sun. After that, you're going to learn the phenomena happening on the surface of our sun with Nabendu Bhaiya, which ended up with a fun activity on coronal ejection. So let's start our journey on how much we know about our sun. You know, from kindergarten, we always fill our sun with yellow color. But is our sun really yellow? Let's see. Before you tell me your perception about the color of our sun, I'm going to show you some images of sun at different time and places. Let's see. See, this is the first image of the common yellow colored sun we always encounter. Now the second one, look, a beautiful image of sunset. Now the third one is the image taken in the space. And now the photo, just look at this neon green color sun. Have you ever imagined that our sun can be so colorful and magnificent? Don't worry. I think just like me, you all still think that the sun is yellow. It's not your fault. Actually, our visuals of color is influenced by many factors like wavelength and intensity of the emitted light, environment, the ability and limitation of our eyes to collect light, and finally our brain. Now I'm going to explain you what's happening in each of these images. Okay, as you see in the first image, do you know why most of the time we always saw yellow colored sun? It's all because of scattering. When the sunlight heat atmospheric particle, it causes electrons and protons to vibrate rapidly ups and down, which radiates the incident light in all directions. And this is what called scattering. Mostly the violet, indigo, and blue light scattered out, leaving most of yellow, red, and orange behind. Now, coming to sunset and sunrise time, as you can see in this picture, in sunset time, the sun is closer to the horizon, which means the light must have to pass through more atmosphere and more air molecule. And with more atmosphere, blue photons get scattered out, leaving behind a lot of yellow, orange, and red spectrum, which gives us an iconically beautiful photographic image of sunset and sunrise. So, till now, all the forms of light and colorful images I show you are the part of the same phenomena, which is called electromagnetic spectrum. Let me explain to you a little bit about electromagnetic spectrum. Mainly, deep inside the sun, a lot is going on. Okay, don't worry. You're going to learn this in a detail with Vaibhav Bhaiya. But due to those reactions, a lot of energy are produced in the form of EM radiation. As you can see in this electromagnetic spectrum scale, there are a lot of waves. Okay, starting from gamma rays to radio waves. They all are put in the scale according to certain pattern. Okay, if you go from gamma rays to radio waves, the wavelength is increasing, and in the same pattern, the frequency is decreasing. But sadly, as we are humans, we are tuned only to see a small portion of this light, okay, which is called the visible ray. Now look at this graph. This is what the complete emission of sun looks like in different wavelengths. As you can see, the peak of this graph is around visible spectrum. Okay, so from this graph, we can conclude that the maximum emission of the sun lies in this visible spectrum of range, and the light comes out is the combination of all these color giving us a white bright light. Actually, if we concluded from this graph, we can say that the color of the sun is white. That this is what you see in our this slide. Just look at it. See the third image. See the third image which were taken in the space is actually shows us the real color of our sun, that is white, because in the space there is no scattering particles or dust. Therefore, the rays of the sun doesn't get distorted and we are able to see the actual color. So don't worry, our science getting so advanced that we are now able to see a lot of other images in X-rays and UV ray spectrum. In this, we used advanced telescope and satellite. For example, the fourth neon green picture of the sun we saw in the previous slide is actually the image was taken by X-ray telescope. And that's all from my part. I hope I was able to clear your misconception about the color of our sun. Now let's refresh our mind with an interesting activity by Anamika.
So good evening, everyone. So we will now start the how to make a pinhole camera. But at first, we will look at the working principle at which our pinhole camera works. The image formed by the camera shows the rectilinear propagation of light, which means the pinhole cameras rely on the fact that light travels in a straight line. When we open the shutter or a window, light illuminates to form an image on the photographic paper or a film placed at the back of the camera. Now I will tell the relation between functioning of the pinhole camera and the functioning of a human eye. It is very closely related. The functioning of pinhole camera is like that of a human eye because in a pinhole camera, the light passes via the pinhole of the camera to project an upside down image onto the back of the box. While in the human eye, light passes through the lens to produce an upside down image on the back of the retina. The brain then flips that image so we experience it with the right side up. Next slide, please. So now we come at the main motive of our activity, that is the experiment, our pinhole camera experiment. So the aim is we have to calculate the radius of the sun using simple household items. And the materials needed are a shoebox, or you can also take a cardboard, a aluminium foil, a sticky tape, a white sheet of paper, a ruler, a pin or a needle. Next slide, please. Now we come at the procedure on how to make a pinhole camera. Uh, First, we have to cut a square out of the center of one of the short sides of the shoebox, place the aluminium foil over the cut out and tape it down. Then use the pin or a needle to pierce the foil, line the inside of the opposite end of the box with the white paper. You now have a pinhole camera. Measure the length of the box from the hole to the sheet of paper. Point the foil-covered front end towards the sun, being careful to never look directly at it as it can harm your eyes. An image of sun will appear on the piece of paper and you can measure it with a ruler. So your pinhole camera looks like this. Now I will tell something about the image formed by the pinhole camera. The size of the image formed by the pinhole camera is smaller than the size of the object and appears inverted on both vertical and horizontal axes when compared with the actual object. The image formed is real because it is visible on the screen or the white paper. The rays coming from the object converge to pass it through the hole of the pinhole camera. The size of the hole determines the sharpness of the image. That means less the size of the hole, sharper the image will be. So next slide. Now I will tell how to measure the diameter of the sun. As you can see in the slide, we can use sun's image size and distance from the image to pinhole you recorded along with the distance from the sun to earth. We can calculate the diameter of the sun. The distance of sun to earth is about 149,600,000 kilometers. That's a huge one, right? So, or we can use the formula diameter of the sun equal to size of the image divided by the length of the box multiplied by the value given, means the value of distance of sun to earth. Next slide, please. The sun's light enters the pinhole and creates an image on the white piece of paper, which you will all do and show your observations to us. Because of the geometry of the setup, we can use ratios to solve for the real sun size. The first ratio will be the ratio of the sun size to the distance between Earth and the sun. That is capital D by capital L. This ratio is equal to the ratio of sun's image size to the distance between the pinhole or the image, that is small d by small l. As you can see, you can also see in the image in this slide to understand more clearly. So here I conclude my activity. Hope I was able to tell you how to make a pinhole camera. So here is one question for you. If you used a pinhole camera to create the image of the candle, what you will notice about the image that is formed? Can you explain why the image is formed the way it is? You can answer in the chat box. If what type of image will be formed?
Okay, we are getting responses. I need more. Respond to everyone, no personal messages. Uh, Baibhav, Ninad has asked, will you please show the previous slide in the diameter of sun? Okay,
Yeah, sure.
Ninad, wait, Ninad, we will be sending you a slide, so don't worry about that. Real image of the candle, the image will be formed upside down, real and inverted. Yes.
If possible, try to ask them the reason also. If they're saying inverted, do they know why it should be inverted? Do you see my slides?
Adarsh is
Yeah,
questioning and
yes, I'm
Adarsh is
seeing.
answering.
Do you see me by any chance?
Yes.
Yes.
Alright. So if the discussion, once the discussion gets over, I'll continue.
Okay, I think Khusbu or Anamika, I think the answers are done in the chat box.
Yes, yes.
Okay, so you all can be more interactive. I don't see any doubts. Either you are understanding everything or you are understanding nothing. So I want more interaction in the during the slides, so you can ask more questions. This will be a little higher level from now. Okay, Beva, I think you can continue.
Sure. Am I still audible? Is my voice
Yes,
breaking or
yes.
something?
No, it's fine.
Okay, great. So, hello everyone. I'm Baibhav and I would be taking you through the next part of our walk through the sun. So, you just got to know that our sun is not the yellow circle we all imagine it to be. It instead has a spectrum with different emissions and different wavelength bands and a lot of energies and a lot of wavelength bands. But the question that should arise now is, why does the sun emit at all? Why does it emit in all those wavelengths, maybe peaking invisible or whatever, but why emission at all? In order to answer a question like this, we should get to know our sun a little more better. And so let's try to take a deeper look into understanding what the sun actually is and what it looks like. So, to the contrary of what one might think, the sun is not a solid object, as you must have understood by now from the first part of the talk. It's actually a huge ball of gas and plasma. If you want to know what plasma is, you would have to wait a little bit more because there is a slide on that later. But as of now, assume that plasma is just a different kind of a gas. So yeah, the sun is a gas, is a ball of gas and plasma, and it's very massive. It's very massive. It's about, if I can give you an analogy, the sun is as massive as 100 trillion Mount Everest kept together. So that's pretty huge. So all these gas molecules, these 100 trillion Mount Everest kept together, all these gas molecules there, they try to move around randomly because of their pressure. They try to move around and move away from each other. But it is gravity that binds all of them together in a very small compact object, which is our sun. So if I can give you an analogy, it's a bad analogy, but still, assume that all the points on this paper, they're gas molecules, and right now they're free. And assume that my hand is gravity now. If you can see my hand is gravity now. So what my hand does is, my hand will compress it into a very small compact object, a ball. Remember that if my hand was not there, it would just open up into a piece of paper. But because of my hand, I can keep it compressed into a small object. And this ball is what the sun is basically. So the pressure and the gravity, they're in a continuous war. The pressure wants to make it expand, the gravity wants to make it contracted, and this war goes on forever. And this is what keeps the sun intact and as we know it. This tug of war between pressure and gravity is very fierce, and it is so fierce that the central temperature of the sun can go up to 15 million degrees Celsius. You can't even imagine how hot that is, 15 million degrees Celsius. Now, if you go on to look at the composition of the sun, it's 70%, about 70% is hydrogen, and 27%, about 27% is helium, and the rest are elements like carbon, oxygen, etc., etc. It's a funny nomenclature, but as anything which is not hydrogen or helium, astronomers prefer to call it as metals. So so only hydrogen and helium are non-metals for astronomers. One thing to ponder about here is, why do you think hydrogen and helium are so important for the sun? It has huge proportions of hydrogen and helium. So just you can put it on the chat, and maybe we'll get to the answer soon. So by then you can put it on the chat. What do you think? Why should hydrogen and helium be important? Okay, so the sun is now a ball of gas and plasma. But is it just that? Is that it? Well, if you see it more, at a deeper level, you'll realize that the things are a little more complicated. Even though it's just made up of gas, it has many different layers, as you can see in this image. The layers can actually be divided into two parts, the inner layers and the outer layers. So the inner layer is actually, it starts with the core. The core is the central region of the sun, and it is the powerhouse. So all the energy that is produced in the sun is because of this core. Just outside this core, you have this orange region, which is the radiative zone. The energy produced in the core, it now tries to move to the next layer, which is the radiative zone again. The energy units, which are photons, if you know what photons are. Oh yeah, okay. So the energy, these photons, they move in a zigzag manner inside the radiative zone. So imagine you are a photon and you want to move out of a room, but the gate of the room is crowded by many people. So what you would do is you would try to find in spaces in between those people. You go here and you find a space at somewhere else. You go here, and this is how you would want to move out of the room, right? This is exactly what the poor photon would be feeling. The radiative zone is so dense that the photon keeps on bouncing off here and there, and bouncing off. And finally, it takes about 1 lakh years for the photon to reach to the surface of the surface of the sun. So, like, pretty poor of the photon. And this actually, the path of the photon is called as the random walk of the photon. So I hope that you get the pun in our talk's name now. So once after the photon has crossed the radiative zone, it enters the convective zone. Once in the convective zone, the energy transfer is very similar to the heating of water. So what happens is the layers which are closer to the radiative zone, they get heated up first. So once they get heated up, they become lighter, they become denser, less denser, and thus they go up. While those regions which were cooler, they fall down. Now the ones which are at the top, they release their energy, they again become lighter, they again become heavier, and they fall back. So I'm sorry, I messed up a bit. So to make it clear again, the radiative zone ends, the convective zone starts. Where the convective zone starts, it's closer to the radiative zone, and the particles there, they get heated up. Once they get heated up, they become light, they go up, they release their energy, and they come back again. So this continues in a cycle. So you go up, you release energy, you become heavier, you come down again, you again get energy, and you keep on going like that forever and forever. So yeah, this keeps on going. After the radiative zone, you have now come to the outer layers of the sun. The first of which is the photosphere. This lies just above the convective zone, and it is the deepest layer of the sun that our telescopes can penetrate. We cannot see beyond the photosphere. After the photosphere comes the chromosphere, just above the photosphere, but this layer is very, very thin, so it's not always visible. Actually, the photosphere is so bright that you cannot even see the chromosphere most of the times. Finally, after the chromosphere, we have the corona, obviously not the virus. It is the hot outer envelope of the sun. It is so hot that the temperature is about 5 lakh degrees Celsius. So it's actually called corona because it comes from a Latin word which means crown. So it looks like the crown of the sun, and thus you call it corona. Between the corona, it's not visible in this image here actually, but between the corona and the chromosphere is a very small region called the transition region. This region is the place where the temperature abruptly rises from 8,000 degrees Celsius of the chromosphere to 5 lakh degrees Celsius of the corona. Okay, so now we have partially answered the question we have started with, that that the sun's energy is produced in the core, right? But how does the core produce this much amount of energy? It is because of a reaction which you call nuclear fusion. To give you an analogy, it's the fusion of Gohan and Trunks coming together forming Gotenks. So what actually happens is the core is so dense, that the hydrogen molecules, they are forced to combine together. They're squeezed together to form a helium atom, giving rise to huge amounts of energy. You can see they're fusing and they're becoming a super Saiyan. If you know what Dragon Ball Z is, if you don't get the analogy, I'm sorry. Yeah, so this actually gives rise to a huge amount of energy. To give you a scale, every second the sun produces enough energy to power the whole of Earth for millions and millions of years. Remember, every second, this is the amount of energy that the sun produces. So the energy is pretty huge. Okay, so now we have our answers. The energy is produced in the core, the energy is produced because of nuclear fusion. But with all these, do you think your image of the sun has changed? Is the sun still the cute little smiling face, yellow circle? Well, I don't know if it's smiling or not, but our childhood images are not very inaccurate. You can still see the yellow photosphere, depending on the filter you're using on the telescope. But if you look at this image more carefully, and even this image a little more carefully, you'll realize that just the internal emissions is not everything for the sun. Not all the light that reaches us is coming from the core of the sun. Things are going on the surface too. As you can see, yeah, okay, you have something on the surface here. You do have something on the surface here too. And this contributes to the sun's emission. So basically, these surface features are a very important aspect of any star and obviously our sun too. These surface phenomena, as I said, they contribute to the sun's emission. And thus, in order to have a complete picture of our sun, we must try to understand what these surface features are. But before I try to I introduce you to different surface features, I must tell you why these surface features arise at all. So the main culprit behind these surface features are magnetic fields. So again, before going on to the surface features, I'll give you a brief about what magnetic fields are. Though by yesterday's discussion, I know that most of you know what magnetic fields are, but still a small discussion. So if you know who Magneto is, he's a villain who is a living magnet. And you can see some field, some lines, something is there around him. And this is true for each and every magnet basically. Every magnet has a field around itself, which is represented by a series of lines. This field is called the magnetic field, and the lines are called magnetic field lines. As you can see, for a bar magnet, it's oval. For a different shaped magnet, the shapes are a little different. As you may know, the Earth even is a huge magnet in itself. You can see the field lines here. You have the North Pole and the South Pole, and the field lines coming out here. Another thing that you can think about is, why do you think the Earth should have a magnetic field at all? Well, yeah, think about it, and maybe we can discuss it in the group someday. And you would get a hint soon, though, about why the Earth should have a magnetic field. Okay, so now, just like the magnetic field of the Earth, the Sun also has a magnetic field. I'm sorry. Yeah, the Sun also has a magnetic field. So remember I talked about those convective packets which were going out and coming back again. So what happens is these packets are packets of plasma moving up and down continuously. When charged particles in the plasma move, they naturally create a very, very strong magnetic field. To give you an idea, this is actually a video of from a very good resolution telescope, of course, the video of the photosphere of our sun. If you concentrate on just some part of it, you would see that some things are coming up and they're sort of dissolving and then they're going back. So they come up, they're basically the convective packets. So the convective packets are coming up, they're giving off their heat and they're going back again to get more heat from the radiative zone. And this continues forever. And this is the reason the continuous flow of the plasma in the form of convective packets and the magnetic fields they produce, these two together give rise to the surface features of our sun. One of the most prominent surface features that we see are called sunspots. And I would be discussing only on the sunspots, and the rest of the surface features would be discussed soon. So wait for it a bit. On our telescopes, they appear as dark spots, dark and cool spots on the surface of the sun. As you can see in the image, you have these dark spots on the surface. But note that these are not static. They're actually changing in size, changing in shape, they're even changing position. So what actually causes them? Again, as I told you, the culprit is magnetic fields. So they're not really very friendly. The plasma which was moving, they gave rise to the magnetic field, right? The movement of the plasma was responsible for giving rise to the magnetic field. But what happens is the magnetic field at times can get so strong that they can exert a force on the plasma itself. So imagine a plasma packet was moving like this continuously, comes the magnetic field and it blocks the flow of plasma. It blocks the convective flow. So the part where it was supposed to go on the surface of the sun, that is now blank. Energy does not reach that part of the surface. And thus what you see is a cold dark spot on the surface of the sun. And that is the reason why we have sunspots. Okay, mind you, when I say that they are cold, the term is very relative here. So it's not like they're really cold. They're cold relative to the other parts of the sun. The other parts of the sun are about 5.5 thousand degrees Celsius, whereas the sunspots, they are about 3.7 thousand degrees Celsius. So there's a difference of about 2000 degrees Celsius, and that's why we call it cold. It's like relative. So with the best telescopes we have, the sun would look something like this. I hope now that we have answered a lot of questions, but before I sign off, I would like to give you a question. I would like to give a question to you all. So there was a recent news, I don't know if you have gone through it or not, but there was a recent news that some activity on the sun was going to affect our telecommunication systems, our navigation and our electrical grids and satellites and all. If you have come across the news, great, but if you haven't, but still give it a thought. How do you think something that is happening on the sun, which is like, the distance now, so something that's happening so far away can affect something on Earth? And again, you can put up the question, you can put up the answers in your chat, and obviously the questions also. And I would hand over to Nabendu Bhaiya for the next part of the talk. So I hope you enjoy. Thank you.
Nabendu, your screen is visible. Audio.
Yes, I heard unmuted. Sorry, I had muted. Should I start now, or we'll let them answer?
Are there any doubts regarding the second part? People appreciated the Dragon Ball Z and Magneto correlation. Other than that, I think no.
Thank God.
Okay, you can start, Nabendu.
Okay. Hello, everyone. This is Nabendu. And okay, is my screen visible in full screen mode, or?
Full screen mode, I can see the eclipsed sun.
Okay, yeah. Okay. So far you have come across some features of the sun, like the color of the sun, its emissions, its how the energy is emitted, some mysteries about its interior structure, and a little bit on the surface phenomenon. Now, at the end, Baibhav posed you with a question that can sun's activity really affect us here on Earth? So, okay, there is an answer that because of magnetic field strength, the radio waves may change their courses and deviate from their paths. Well, yes, that's roughly true, and we'll be discussing more on that. And I'll be discussing in particular a phenomenon which is so intense that it can really affect life here on Earth. And for some reason, okay, yeah. So that is called coronal mass ejection. Now, what is coronal mass ejection, or in short, CME? CME is a large eruption of magnetized plasma from the outer atmosphere of the sun, which, as you have already known from Baibhav, is called corona. It is not a continuous feature of the sun, rather it happens transiently. So we call it, it's a transient feature of the sun. And these coronal mass ejections are found by explosive reconfigurations of solar magnetic fields, which in technical terms are called magnetic reconnections. And coronal mass ejections often follow what are called solar flares. Now, I understand that some of the terms that I have used here might seem very complicated to you. So I would explain you one by one what they mean. So first I told that a CME is a large eruption of magnetized plasma. Now, what is plasma? In simple terms, plasma is a state of matter which consists of positive ions and free electrons, which have been stripped apart from their parent atoms. And this plasma is formed at extremely high temperature. So to give you a comparison, you already would be familiar with the states of matter: solid, liquid, and gas. In solid, as you know, the atoms are very tightly packed, and in liquid, the arrangement is slightly more loose, and in gas, the atoms move randomly, and the arrangement is very, very loose. Now, the difference in plasma is that uh, from these randomly moving atoms, if you increase the temperature to very high temperature, if you go to very high temperature, these neutral atoms can get ionized, and as a result, what you get is positive ions and free electrons, which are of course negatively charged. So, in short, plasma is a gas of ionized particles, both positively and negatively charged particles. So this is all about plasma. Then secondly, I told that a coronal mass ejection is a transient feature of the sun. Now, what does transient mean in the context of sun? So you would have already heard from Baibhav about solar activity, the energy output and its magnetic fields and all. And you would have already known that the magnetic field activity is related to sunspots. So this is a curve that shows number of sunspots versus time. So the x-axis shows the year, as you can see, from 1985 to 2020, and y-axis shows the number of sunspots. And the curve the curve shows that in the initial time, that is in 1985, the number of sunspots is very less. It's the minimum. This suggests that the solar activity or the energy output, or you can also say energy output, solar activity or magnetic field activity, was lowest in this period. Now, with time, it gradually increased. So the number of sunspots also increased, and it reached a maximum in around 1991. So, and again, the solar activity and the number of sunspots decreased, and it reached minimum again in 1996. So the point here is that the solar activity or the energy output of the sun is not constant, or it's not a continuous process. Rather, it happens in cycles. And the period of the cycle is around 11 years. So you can see a minima happening, then maxima, then minima again, and the whole period is about 11 years, and the same cycle repeating again. As I already told, the sun's magnetic field strength, it undergoes. I request everyone to please mute their audio. The magnetic field strength undergoes a cycle every 11 years, and solar maxima is the period in which the number of sunspots and solar activity is highest. As I showed you in the previous curve, this is the solar maxima. And similarly, solar minima is when the number of sunspots or solar activity is minimum. Now, how is it relevant to our discussion of coronal mass ejection? Well, it is like this. During solar maxima, the number of sunspots and the solar activity is so high that coronal mass ejections, about 3 coronal mass ejections can happen every day. But on the other hand, during solar minima, the number of sunspots and correspondingly the solar activity is so low that only 1 coronal mass ejection can happen in around 5 days. So that's what I meant when I told that coronal mass ejections are not a continuous process, rather they're transient in nature. Next, I told that coronal mass ejections are formed due to something called magnetic reconnections. Now, magnetic reconnections is a bit complicated, so I would take a while to explain what it is. Again, to state in very simple terms, it is the breaking and reconnecting of magnetic field lines that are oppositely directed. So this animation will help to illustrate this phenomenon better. As you can see, the red and blue field lines are oppositely directed. Okay, let the animation repeat. So here you can see they are oppositely directed, and when they come together, are nearby each other, they can come, break apart, and get reconnected. As you can see, they come together, they break apart, and they get reconnected again. And when they get reconnected, the overall configuration of the magnetic field lines changes. So something similar happens on the surface of the sun. And this is just a cartoon representation of the sun, the surface of the sun. These maroon spots are the sunspots, and the black curved lines indicate magnetic field lines. As you can see, the magnetic field lines here are pointing downward, and the magnetic field lines here are pointing upward. So here also, 2 sunspots, or you can say group of sunspots maybe, when they are nearby, the magnetic field lines will be oppositely directed like this. And when they come together, when they come nearby in vicinity of each other, the similar kind of magnetic reconnection process can happen. They can break apart from in between, and they can get reconnected in a different configuration. And when this kind of magnetic reconnection happens, what also happens is some of the magnetized plasma gets stripped apart from the surface of the sun. As Baibhav told you, the surface of the sun is is not a very quiet place. It's full of activity. So there are plasma present there on the corona, and when magnetic reconnection happens, this kind of plasma packets, they can also get ejected from the surface and they move outward. And this whole process is called coronal mass ejection. The coronal refers to the surface, corona, and mass refers to this plasma, magnetized plasma, and ejection means since they are being ejected away from the sun. Now, at the end, I told that these coronal mass ejections often follow solar flares. Now, you would be wondering what solar flares are. See, so solar flare is a sudden flash of increased brightness on the surface of the sun. And these are observed close to the sunspots on the surface. And one point to note is that these solar flares may or may not be accompanied by a coronal mass ejection. Now, this is an animation of solar flare. You can see suddenly there is, from this part, there is increased brightness and some gases also being ejected. Now, the difference, I have a question which I will ask. I will ask it now. So, from what I have told you till now, what do you think is the difference between solar flare and coronal mass ejection? Meanwhile, I will go through my talk and you can answer this question in the chat box. Okay, so continue. Now we'll be talking something more about coronal mass ejection. The ejected plasma from the surface of the sun, the ejected plasma of a CME can travel faster than the accompanying solar wind. Now, the solar wind is just a fancy term for the stream of particles that are ejected from the sun. When this ejected plasma travels faster than the solar wind, it can produce shock waves. Now, you might not be familiar with shock waves, so I will take a little bit of diversion to explain what they are. Shock waves are disturbances that travel faster than sound waves. And something that travels faster than sound waves, we call them supersonic. So here you can see in the first image here, the dot at the center represents the source of sound. And the circles surrounding it, these represent the disturbances or the waves. So you can see for a stationary source, a source which is not moving, the disturbances around it are perfectly circular. And in this image, you can see the source is moving, but it's moving with a speed which is less than the speed of sound. So the disturbances are not symmetrical as it was in the case of stationary source. Rather, it is a bit distorted and the disturbances are something like this. Now, this is the case when source is moving slower than the speed of sound. But in some rare cases, the source of sound can actually move faster than the speed of sound itself. So when that happens, the source can get outside the circle of the circle that contains that represents disturbances. So when this kind of phenomenon happens, it produces shock waves. And for you, just the important point is that shock waves travel faster than the speed of sound in that medium. And from our discussion, the relevant thing is that sometimes this ejected plasma can travel faster than the solar wind, and thus they can produce shock waves. Now, when coronal mass ejection, along with the shock waves, travel towards the atmosphere of a planet like our Earth, they can disrupt the electromagnetic fields that are present on the planet. Now, Baibhav has already explained what magnetic field is. Similarly, there is also an electric field, which is the field that is created because of in the presence of electric charges. And electric and magnetic fields are connected. They're very much related to each other, which you will be learning as you go higher in your studies, if you opt for science or physics. And these electromagnetic fields of a planet can get disrupted by coronal mass ejection. Now, Baibhav posed you with a question that if solar activity can have any impact on our Earth? Well, as a matter of fact, they do have an impact. So as I told, the coronal mass ejections carry along with it magnetized plasma. So magnetized plasma means it also carries some magnetic field around with it, along with it. So when such a magnetic field or a part of magnetic field comes and enters the atmosphere, and Earth also has a magnetic field. So these two magnetic fields can interact, and the magnetic field that is present in the Earth can get disrupted. Now, this can lead to a variety of phenomena on different scales. And one of these is called geomagnetic storms. Now, geomagnetic storms can be pretty violent. And historically speaking, there have been very dangerous geomagnetic storms in the past. Secondly, coronal mass ejections can cause electrical grid failures. And as I told you, magnetic field and electric fields are related. So when there is disruption of magnetic field, that must be disruption of electric field as well. And thus we get grid failures of the electrical field lines and also telecommunication lines. And thirdly, coronal mass ejection can lead to extravagant forms of aurora. Uh, this is an illustration of how the magnetic field coming from the sun can actually disrupt the magnetic field on Earth. You see magnetic field packet coming from the sun, and it disrupts the magnetic field on Earth. And near the poles, you can see some bright lights, some bright display of lights. You can see it again. The magnetic field lines from the sun disrupt the magnetic field lines of Earth, and due to that, the some of the gases present in the atmosphere can get ionized, and the energy that is carried by the magnetic field or the coronal mass ejections, these excite these atoms present in the atmosphere of Earth, and when these atoms de-excite, they emit light. So all these terms might be very confusing for you, this excitation and de-excitation. So for you, what is important to know is that magnetic fields coming from sun can affect the gaseous particles present in the atmosphere, and they can lead to emission of light. And this happens mostly at the North Pole and the South Pole of Earth, because that is where the magnetic field strength is highest. And aurora is one such example that happens on the poles. It is a beautiful display of lights, which I explained are caused due to the excitation and de-excitation of atoms, and followed by emission of lights. And usually solar wind, which I told that are just a stream of charged particles from the sun. The solar wind can cause aurora on a regular basis in the north and south poles. However, a coronal mass ejection can cause this kind of aurora, but very extravagant forms of aurora, which are seen even in the lower latitudes, not only in the north poles. Now, this is what I had in the form of a lecture about sun or the coronal mass ejection. Now, I'll be taking you for a fun activity. And before I go to the fun activity, I wanted to know that in NASA there is an observatory called Solar and Heliospheric Observatory, whose job is to take images of the sun in various wavelengths. But our focus here is on one of these instruments, which is LASCO instrument. Now, LASCO stands for Large Angle and Spectrometric Coronagraph Experiment. And this is an image of that LASCO experiment. Okay. So what does this instrument do? The job of this instrument is to take images of this kind of images. Now, what is this image? In this image, you can see the white portion here, the whitish like gaseous-like thing here is actually a coronal mass ejection. So LASCO instrument takes pictures or images of coronal mass ejections from the sun. And the white ring here indicates the circumference of the sun. And this black disk is called occulting disk. Occulting means to hide. Now, what does this occulting disk do? This occulting disk actually hides or hides the brightest portion of the sun. Now, why is that needed? So it is something like this. When you have a bright source and you need to see something very less bright or slightly dim around it, you need to hide that bright portion, right? So that you can see the dimmer portions surrounding that bright portion. So this is exactly what happens here. This black occulting disk hides the brightest portion of the sun. So it is something like this. So this is an image of the sun, and you can see surrounding is the surface phenomena taking place, and this gives an indication of the circumference, this white ring. Now there is a black occulting disk. Now this occulting disk, what it does is that it hides the brightest portion. So that helps us to actually view the surrounding portion or the corona. And that is, we do that because that is how we can image a coronal mass ejection. So that is roughly what a LASCO instrument does. Now we come to the activity that we have for you. And this is a series of images that have been taken from this LASCO instrument. And these images have been taken at different times. You can see that time is mentioned at top. It is at 8:05, then 8:36, 9:27, 10:25, 11:23. Okay. So the step one, okay. First, I would let you know what our aim is in this activity. Now, our aim or objective is to track a coronal mass ejection. So a coronal mass ejection that is happening from the sun, from the surface of the sun, you can track its position, its actual position, its actual velocity, and at what rate it is accelerating, or increasing or decreasing its speed. So all this you can do through this simple fun activity. Now, step one of that is to track its position. Now, in doing that, this is the formula that will help you. This is almost similar, very similar, or I should say exactly same formula that you would have seen in first activity that Anamika explained to you. So, and this is the proportionality formula. The ratio of actual diameter of the sun to the ratio of the diameter that is observed on screen to the actual diameter of the sun is the same as, is equal to the ratio, the position of a mass that is seen on screen to the actual position of that mass. That is what this proportionality formula is. And now from this series of images, what you can do is there is a scale that you can see at the bottom of each of these images. So this scale, okay, so what we will do is you can find the diameter, how much the diameter is on this scale. The diameter of this ring you can find according to this scale. Say this is about how much? Diameter is about this much. So it is around, okay. So this is 1 unit. This much. So the diameter of the sun is 1 unit on this image. So that is what is the D screen. Yes, for some reason, I'm not able to change my slide. Just a second. Okay, yeah. Sorry for the delay. D screen is the diameter of the sun as measured on the screen. So as I showed you, it is 1 unit. And D actual is the actual diameter of the sun. Now the actual diameter of the sun you can get as a result of activity 1 that has been explained to you. So you'll take the diameter of the sun from that actual diameter, then D screen or the diameter of the sun measured on the screen, you will get as I showed you. And similarly, you'll also find S screen. Now S screen is this. You will take one position on this, you'll select one mass on this image. Say you select the point which is the so the exterior most point here. Here, this one, the exterior most point of the coronal mass ejection. Then you will see, you will take note of what the position of this point is on this scale. So this comes roughly to here. So the position, it is around 1, 2, 3, 4, 5, 6. This is around 7th unit, or you can say if this is not a full unit, this is a half unit. So 6.5 unit. So the position is 6.5 units on this scale. So you know S screen, you know D screen, and you know D actual. Now using this formula, you can get S actual. Now S actual will give you the actual position of that mass in space. So by this way, you know the actual position of that mass you have considered in the first image. Now you will repeat all this for the second image, and similarly for third image, and so on. Now after this, what you will get is you would be having 5 times this 8, 5, 836, 927, 1025, and 1123. And you would have got 5 positions, the 5 S actual for each of these images. So you take note of all this, and then we move to step 2. Step 2 is to calculate the velocity of the coronal mass ejection. And velocity is, as you know, the rate of change of displacement. And the formula for average velocity is S2 minus S1 divided by T2 minus T1, where S2 and S1 are the positions at time T2 and T1 respectively. Now, how do you calculate velocity? So first, so you would have already got the positions and you know the times. So you just need to use the formula for velocity. So corresponding to this 5 to 836, you can get one velocity. Let's say that velocity is V1. And then corresponding to the second and third images, that is T2, between T2 and T3, you can get another velocity, say V2. Then between second and third image, sorry, third and fourth, you will get V3. And between fourth and fifth, you will get V4. Now for 4 images or for 4 positions, you can get, you will get 4, sorry, for 5 positions, you will get 4 velocities. Now the next step is to find acceleration. And acceleration, as you know, is the rate of change of velocity. And the formula for acceleration is V2 minus V1 by T2 minus T1. So after getting 4 velocities, you can similarly get calculate the acceleration for each of these 4 velocities. That how you will do is between V1 and V2, you can get one acceleration that will be A1. Then between V2 and V3, you get another acceleration that is A2. And then finally between V3 and V4, you'll get another acceleration, which is A3. So finally what you have is, there are 5 images, correspondingly 5 different times. And from these 5 times, you can get the position of a mass or coronal mass ejection at these 5 times. So you have 5 positions, and you have 4 velocities and 3 accelerations. Now, whatever result you get, you will tabulate this. And we will be sharing a detailed procedure with you all, a document carrying the detailed procedure and the table that you need to make. And we'll also be sharing with you a Google form in which you have to send us your answers. So this is a fun activity that you can do to track the coronal mass ejections.
Okay. Thank you, Nabendu.
For some reason, again, my slide is not changing. But anyway, I was at the end of my talk. So
Okay. Okay.
thank you very much.
So I hope that most of you got the main part of the talk. Still, if there are any doubts, you can ask in the chat box if we didn't see any. Or you can ask now in the chat box, or if there are any major doubts, you can unmute yourselves. If there aren't any, I want to ask it to the students. Tell me two sentences, exactly two sentences of what is a CME. Anyone can unmute, but uh, only two sentences. What is a CME? Coronal mass ejection. Make sure your interaction is being recorded and graded. So, uh, or you can type if you are hesitating to talk. I think the first day went a little hard. Just to summarize, a CME is a mass of plasma. Plasma was explained by Nabendu as a gas of charges. So most of you must be knowing what is a plasma. Create a plasma that comes out from the sun and goes into the interplanetary medium. So this is a two-line answer. Um, you can refer more in the sources that will be given in the end of the slides. And I think the activities are fun and they can be done if you follow the procedure. Still, if there are any other doubts, you can contact us in the WhatsApp. Please be free. We want people to literally ask as many number of doubts as you can in the chat box or at the end of the talk. So, and we are not, sir, we are seniors to you as a bhaiya or didi. Okay. Um, there are few more announcements that I would like to make. Uh, these two activities that you have been given will be submitted by you by the end of this Saturday, that is 7th. So those who submitted by 7th will be uh, for activities also you can ask any doubt as Avinash said. So if for activities you have to submit it by 7th, these your results will be graded as per the accuracy. But still, as there is no one correct answer for any of these activities, there can be a margin of correct answers. So don't copy, have fun making a pinhole or just using a ruler and finding what is the velocity and acceleration of CME. If you don't know, don't exactly know what is a CME, just take it as an object that is moving. So I think you all know how to calculate velocity or acceleration of anything. Okay. Um,
Bhaiya, is it compulsory to do the activities?
Yeah, it is compulsory to do the activities. As we mentioned in the group, there will be three kinds of certificate: participation, merit, and distinction. So depending on your result and depending on your participation, we will be deciding who will be getting what. So
And Bhaiya, can you please send the activities in the group?
yes, we will be mailing everything. We will be mailing the slides and the activity form procedure to everyone in the mail.
Okay, sir. Okay, Bhaiya.
Uh, there are a few comments in there. Do you have to take a photo of the pinhole and send? No, you just while doing the activity, you can share the photo of you doing it so that we can feature you in our Instagram or in the website at the end of this event. So that would be good for us. And Nabendu, you can select any point on the CME, but make sure that you are tracking the same point through all the images. Yes.
I was just giving them a hint about the activity.
Okay. And one more announcement for you all is regarding another group in our NOX. So Shailaja or Gayatri, you may take over.
Okay, so we have a fun event planned for you guys. So basically, soon we are going to have a debate held, and this debate is uh, okay. So basically, we are going to have a debate for you guys. This will be held in the next week. This week you will be getting your registration links, and I hope most of you participate. So basically, we are planning on holding the debate in 2 rounds. The first round is going to be on WhatsApp, and the second round will be informed to you in the process. And I hope a lot of you participate in this event.
Okay, thank you. And apart from these two activities, from the Pinhole, the CME, and the third thing, that announcement of debate, there is another activity which is rather fun activity than a lot of thinking, which is named scale model. So you all must be knowing that the solar system, the 8 planets, have different sizes of planets, and the distance of the planets from the center is different. Right? From the center means from the sun is different. So that is a very there is a very huge difference, a huge gap between planets that people really forget to appreciate. So for that, we are giving you another activity that will be submitted by you before Saturday, that is 7th. The name scale model. The main motto or gist of the activity will be that you will be making small paper cutouts of 5 to 11 cm. There is a different range of different planets, and you will be placing it on the floor and just giving us the photographs showing us the relative sizes of the planets and relative distances of the planets. We will be sending you a procedure and a Google form for everything by mail. So keep checking your mail. And I think you are still processing many of the things that happened today. You can ask silly doubts even from the start in the WhatsApp, or you can message any of the coordinators in the group. So coordinators are mainly the people who are owner of the group. So you know Nabendu, Baibhav, Anamika, and Khusbu. These four were coordinating today. So you can ask these four, or me, or Kinkini, or Mekla, and we will be there to clarify your doubts. So I think there are no more things that needs to be announced today. Or if I am forgetting anything, Kinkini or Mekla, can you remind me? I think no. Another thing with Abhinash pointed out, this recorded lecture is in the YouTube channel. We will give you the link so you can refer to it again. Okay, so I think we can end it today. Thank you everyone for joining. I hope you all participate actively in the activities, in discussions, in debate, in quizzes, and also in all other talks. Two more to go.
Adarsh, was today's session supposed to end so early? I mean, what was the time? How much time do we have maximum, or is it supposed to end now?
It is supposed to be end now. Means
Okay.
there is nothing else to do. Okay, so today's talk was in time. So yeah. So thank you everyone. We will meet again on next Sunday.